So let's come back and study our leading order Lagrangian. And actually, we've already learned something about factorization, although we don't know it yet. So what is this word factorization? One way of thinking about what factorization is it's how different degrees of freedom talk to each other. And given that we have a leading order Lagrangian for the collinear and ultrasoft fields, we should know something about how collinear and ultrasoft fields talk to each other. So let's come back and study LCC0. So the propagator, if we write out what the propagator is, if we're careful about signs of I epsilons, we had both particles and antiparticles. You can think of the antiparticles as the guys that have the minus I0. And if you combine these two things together, then that's just giving you the thing that we got when we expanded QCD. So when you think about deriving it from the SCT Lagrangian, you think about getting this piece, but then you have to also sum over the other pieces with the other sign of the m bar dot p, and you get this piece, and they sum back to that thing. Okay, so this is the particles. If I want to split out the particles and antiparticles, I can do this. This is the particles that have m bar dot p greater than 0, and this is the antiparticles. Then in this notation, where m bar dot p follows the fermion line flow, we have m bar dot p less than 0. OK, so that, in some sense, we already alluded to that the propagator works out correctly. This is showing it explicitly. What about interactions? Well, I want to be interested in a minute about ultrasoft interactions, because they're kind of special. For the ultrasoft gluons, only n.a ultrasoft showed up at leading order in the LCC 0. So if we look at the Feynman rule there, we have this, let's give this guy an index mu, and this guy's ultrasoft, this guy's n collinear. Then the Feynman rule just has n mu in it, not gamma mu. Okay. So that's an observation that we know from our LCC 0, and that just comes from, remember, this just comes from the in.d term, because that's the only term that had the ultrasoft gauge field in it. But there's another fact that our Lagrangian told us, and that is that only the n.k ultrasoft momentum, so if I call this momentum k, only the component n.k was also showing up in the propagators. So there's a gauge field statement as well as a statement about the ultrasoft momenta. And that was due to the multipole expansion that we did. So if we do that at the level of thinking about some kind of diagram, so let's think about some type of diagram like this, and let's look at this propagator here. That propagator we wrote this out before, but let me write it out again. So if I say P is this guy and K is this guy, then this guy's P plus K, but K being ultrasoft, these guys are supposed to be ultrasoft, let's say. K being ultrasoft, only the n.k shows up in that propagator. And if we work on shell, where p squared is 0, so let me first rewrite this so that you can see where I'm going. I can form a full p squared in the denominator from the terms that depend on p. That's just the full p squared of the particle. And if this guy is an external particle, as it is in my figure, then p squared would be 0. Okay, so if I go to the on-shell case, p squared equals 0, then this just becomes n bar dot p, n bar dot p, n dot k plus I0, which is looking like just 1 over n dot k. So it's becoming very simple. For collinear gluons, it would of course not be, there would be no simplification like that possible, but for the ultrasoft particles there is. And so what has just happened is that the propagator is becoming iconal. So our collinear propagator reduces to the iconal approximation, which is just 1 over n dot k, when appropriate. And when appropriate means when it's interacting with ultrasoft fields. So we can kind of summarize that for all the different possible cases in the following way. So you could have, if you want to be careful about signs, you could think about attaching ultrasoft gluons to a fermion coming in or a fermion going out, or likewise to an antiparticle coming in or going out. And you always take k going up. And if I work with the external particle on shell, then combining together the Feynman rule for the vertex and the rule for the propagator, I'm getting these what are called sometimes iconal vertices or propagator vertices. So these are iconal. Iconal in both the interactions and in the vertex. And that's what should happen for having a very soft particle talking to something very energetic. That's called the iconal approximation, and it just falls out of our effective field theory. So this can actually lead us to something deeper, which is called Ultrasoft-Collinear Factorization. So let's consider more than one gluon. We'll have one collinear fermion, and we'll just attach a bunch of ultrasoft gluons to it. So in kind of obvious notation. Let's call it M. So we could sum up those diagrams. And if we sum up those diagrams, we get something that looks familiar. So sum over M, sum over permutations, some factors of G, gauge fields. Okay. Be careful about ordering. And I'm working here on shell. So the external collinear particle has p squared equals 0. So if you think about what this is, it's just a Wilson line. It's not the same Wilson line that we were talking about before. This Wilson line is built from ultrasoft fields, not collinear fields. And it doesn't even point in the same direction. It points in the n direction, not the n bar direction. But it is a Wilson line. Yeah, I think so.
I think you might have minus sign errors in the top of the board.
So for this guy, there's no minus sign error because, well, I didn't tell you what the proportion, like, there could be a minus g or a plus g here, right? Yeah, that's minus g probably. Yeah. Okay. So actually what this motivates us to do from the effective theory point of view is to consider the following. It motivates us to think about making a field redefinition. Because what we just did is we iterated the leading order L0 Lagrangian over and over again to get these vertices as well as the propagators. And we ended up with something that was just a Wilson line. Could we capture that somehow in a simpler way? And the answer is yes, if we make the following field redefinition. We take our original CNP field and we pull out a Wilson line Y, and we can do a similar thing for the gauge field. This is just the adjoint version of the same field redefinition, where Y is a Wilson line, which corresponds to that in momentum space and in position space. It's a path-ordered exponential. Like that. So when I say that the Wilson line's at x, that means I've shifted the whole line by x. Okay, and I could just denote that by putting an x here. And then from that point in space-time, there's a line going out in the n direction. That's what this formula is saying. So at s equals 0, then you just sit at x. Okay. So this should be your picture. Oh, this is minus infinity, so it's not a very good picture. And so this Wilson line, like any Wilson line, has an equation of motion, which is this. It satisfies y dagger y is 1. And if you go through with our transformation for the collinear gluon, which I could have also motivated in this way, if I'd gone through the calculation where instead of having a collinear quark here, I had a collinear gluon, I would have found exactly the same thing, except all these a's would be in the adjoint representation. Well, I didn't write the t's anyway, so. All right, so either the fundamental representation or the adjoint representation, and that would motivate you to make the same type of field redefinition to try to capture what's going on there. Okay. So let's see what that does to our Lagrangian. So our original Lagrangian, I'm not going to write out all the terms, just enough terms to get you the idea. If I make this field redefinition, it goes to this guy with a superscript 0 that I'm writing. And then let me write out here, let me split this derivative into two pieces. So I'm still not writing the terms that are in the dot. So what I did is I took the y from this guy and the y from that guy, put them inside the square bracket. This n dot d, remember, has two pieces. It's I n dot d is sort of an I n dot d ultrasoft, which just has the ultrasoft gauge field, but then there's a piece that involves the collinear gauge field. But then the collinear gauge field also transforms, as I wrote up there, so I get this y dagger for that guy. So for the collinear gauge field, these y's are canceling. And this guy here, if you push the derivative through the y using this formula, then the y's are also canceling, and this is just becoming I n dot partial. So that's becoming I n dot partial, and this is becoming n dot a n of 0. So what's happening is that the ultrasoft gauge field is dropping out. Now there's terms in the plus dot dot dot. Those terms involve the d perp slash and the 1 over m bar dot d. And if I had written out those terms too, then the same thing would happen actually. They would all the y's would cancel out in those terms as well. So what I'm getting here is something that I might call an n dot dn. It's a covariant derivative that only involves the an0 field. And there's actually no ultrasoft fields at all left in the Lagrangian after I make this field redefinition. So that's obviously giving us a much simpler Lagrangian. OK, so it looks like a good thing to do. And that, if you go through it, is actually true also for the gluon action. The gluon action was also built of n dot d type fields, type covariant derivatives. That's where the ultrasoft gluon showed up. And basically, same thing happens. This same relation right there means that the ultrasoft gluon would decouple from that Lagrangian as well. So making this field redefinition, we actually decoupled in the Lagrangians the ultrasoft and the collinear fields. So even though the effective theory allowed these modes to couple to each other, they coupled in a very simple way. And so what we're saying is that it's convenient because they couple in such a simple way. If they didn't couple in such a simple way, we would stop and we just use that Lagrangian, we do physics. Since they do couple in such a simple way, we can do physics in terms of some reparameterized variables or redefined variables, which are these new variables. And that's convenient because now, if I think about our original Lagrangian, it goes over to something that looks much simpler, because it's going over to something that has no, for the L0, has no ultrasoft fields. This wouldn't be, of course, true for the L1 or higher order Lagrangians. It actually would still simplify those Lagrangians in a certain way. But for the leading order one, it seems to make a dramatic simplification because we no longer have this coupling. So you might think, well, the interactions have all disappeared. But they haven't disappeared, because when you make the field redefinition, you can't just make it to the Lagrangian. You also have to make it on operators in the theory. And what this does is it moves some interactions out of the Lagrangian and into currents. So let's do some examples of that. Since it's for the Lagrangian, it's always the same. That's one of the reasons why this is powerful, because we just do it once and for all. We just did it for the Lagrangian. And then we can see what happens for a bunch of different currents. So I'll do 3 examples. So one example that we had was this current for e to s gamma, which had a heavy quark field and one light collinear up quark and a Wilson line. I should have said another thing that I'm using, which is important, is that if you go through what, make sure I get my y's and the y daggers on the right side. If you go through what happens for the collinear Wilson line after the field redefinition, this guy, remember, is written in terms of these fields. And this guy here is written in terms of those fields. And it also gets y's on the outside. That's important when you start considering, for example, these dots. OK, but I need that here. So given that that's also true, if I want to look at this guy, just make the field redefinition. So I get this. I get a y dagger on both sides of the Wilson line. These guys cancel each other. This is a Wilson line 0. So I have C bar 0, Wilson line 0. And I have gamma. And I have y dagger HV. So now I have a Wilson line sitting next to the heavy quark and another Wilson line sitting next to the collinear quark. So if you think in the diagram that we drew, the interactions that were those gluons attaching to the collinear quark, they're now just all represented by this Wilson line here. But it's even more than that, because we also transformed the Wilson line. So even if we'd attached ultrasoft gluons to that Wilson line, they all magically simplify into one simple Wilson line, y dagger. So from a diagrammatic point of view, if we'd actually tried to carry out the calculation that would give this formula, it would be kind of horrendous, because there's an enormous amount of cancellations going on to give this. It just looks complicated in the diagrams. But here it looks very simple. And the fact that the leading order Lagrangian gave us 0 there tells us that that it really is the sum of the diagrams. Let's have a couple more examples. So you could take our example for 2 jets. And you could ask, what would happen in that case? What's the generalization if I have more than one collinear direction? And the generalization is that you just make the same field redefinition, but it's a different component of the ultrasoft field that couples to different collinear fields. So you're making a field redefinition that's appropriate to each of the different collinear sectors. But other than that, it goes through the same way. And so here, this yn1 dagger involves n1.a ultrasoft fields, and this guy here involves n2.a ultrasoft fields. And they don't cancel, but they do simplify. All the interactions in this case simplify to this simple y dagger y combination. OK, so having more than one collinear direction is not, it means that you have more than one type of y showing up. But again, it's just the leading order Lagrangian for each of those sectors that tell you what's going to show up. Type of y. Let's do one more example. Let's do an example where we have collinear fields that are in the following form, where both directions are n. And we have an operator like that. So it's the same operator I was writing down here, but in this case I had n1 and n2 for 2 jets. I haven't really told you about an example that would involve this operator here, but it turns out this operator here is something that shows up, for example, in a part-time distribution function and other places. So this operator also does make an appearance in physics. And if you look at what happens for this operator, all the y's cancel. So when we go through the transformation, we have y dagger, but then the y's exactly cancel. So in that case, it's really true that the ultrasoft gluons are dropping out once you effectively, when you add up diagrams, that there's no ultrasoft gluons left. In these cases, that's the leftover is these Wilson lines that are showing up in the operator. In this case, there's no leftover. Okay?
Are those both valued at the same position?
Yeah.
Why are the W's?
Because, yeah. So they would if I just wrote this. In general, what you could have inserted in here is some kind of something that picks out like the momentum of one of those W's. So let me just throw that delta function in there so they don't cancel. We'll talk about that in a minute or two. Yeah, but in general, I could cancel them in this particular formula. But there's reasons why actually we won't want to cancel them, because we will be putting other things in between that won't change what I just said. So imagine that you had something that measured the momentum of one of these products of fields. It would still be true that these y's, which are not having labels, would cancel in the way that we said, but the w's wouldn't cancel. OK, so this is called the BPS field redefinition, and S is me. And this thing sums up an infinite class of diagrams. What it does in example 1, if you want to think about what the diagrams would look like, let me draw kind of an example for you. So let's have some collinear particles. And just to make it look non-trivial, let me draw something that seems kind of non-trivial. So there's a bunch of collinear particles. And then we could add ultrasoft gluons to them. And the ultrasoft gluons can couple to all those collinear particles, the gluons, the quarks, everybody. If we consider all the ultrasoft gluons coupling to the collinear particles everywhere, and we add up all those attachments, then it just becomes a single Wilson line. So this thing becomes a single Wilson line, and then times exactly the same collinear structure. So what I'm saying doesn't rely, since we did it at the level of Lagrangian, it doesn't rely on whether or not they're loops or tree level or anything like that. So this diagram there, if we add up all possible attachments, will be equal to that one, where this is a y. In this case, it's a y dagger. OK, so that's the simplicity encoded in this formula right here. This is an example with J1. In example 3, then it's a little simpler even, because the ultrasoft gluons are decoupling at lowest order. From any graph that you might consider. So you go through the same exercise, but now that the y's are all canceling out. And this has a name that sometimes people use called color transparency. So one place that it shows up is the following. Let's take our current J3 and imagine that we produce from that current an energetic pion. That was one of the examples we talked about when we were talking about V to d pi. So there's a collinear pion. And these are collinear quarks, collinear quark and antiquark. So they're supposed to be inside the pion. And then there's collinear gluons. If we attach all the ultrasoft gluons to this object, then the Wilson lines cancel. So the ultrasoft gluons are decoupling from energetic particles. And the reason that they're decoupling is because the partons here are in a color singlet state, which is this pion. Okay, so here we're producing a color-neutral pion out of color-contracted collinear quark fields. And there's these Wilson lines, for reasons we'll discuss in a minute, how they kind of play a role in physics here. But the reason that the Wilson lines are canceling is because the collinear things were already contracted. All the collinear things in the n direction were contracted in a color singlet, global color singlet. So the words that go along with this phrase, color transparency, is that you have these very soft gluons, and they're trying to come in and see this thing. But they can't really, all they can see is sort of the overall color charge of the whole thing. They couple kind of, because of the multipole expansion, they're only coupling to a sort of single component, and you can think of that as if they're only seeing an overall color charge. And therefore, since its overall color charge is neutral, you don't see, they just cancel out. Okay. In my notes, I also have a page talking about how you could think of gauge transformations after making this field redefinition, but it's kind of an aside, so I'm not going to talk about it in lecture. But I will post it.